Uh, Good day, Prof. My name is Ming Feng, and today I will explain the assignment bin for this question and to design the bin DE from the level 1 by given the data here in the simple construction. Okay. So first, I will calculate the load distribution, okay, which is one way, and then I draw it here. Then the permanent load and the variable load is given. Then I using this formula to get the design load is 12.75 kN per meter cube. So first I will calculate the load from the slab 1, 2, 3, which support by the secondary beam. So I will multiply the area of the slab. So I get the total design load is 63.75 kN. Then the shear force by using this formula to divide 2, and I get the answer is 31.875 kN. And because of the secondary beam support, the slab is both is the same area. So just multiply 2 to get the shear force, total shear force. And because the secondary beam 1 and the secondary beam 2 is the same, yeah, so it's direct. I put 63.75 kN. So after secondary beam is calculated, so now it's analyze the beam DE. So first I will calculate the self width of the brick wall, which given the data 3 kN per meter square, and I multiply the height from the level 1 is 4 meter. Then I get the answer, and then I calculate the uniform load. Uniform distribution load is 16.2 kN per meter. Okay, then by using the load from the slab, I multiply the width of the slab, so I get 12.75 kN per meter. Then I total up the uniform distribution load from the slab and the self width of the brick wall, and I get 28.95 kN per meter. Then I combine all the information that I calculate. So this is the secondary beam with the load 63.75 kN, and this one is secondary beam 2, and this is the uniform load from the slab and the brick wall. So I using this method to calculate the reaction force at the D and E is 150.6 kN. Then I draw the shear force diagram and the bending moment diagram to obtain the maximum shear force and the maximum bending moment. So after that, I will determine the trial section by using this formula to get the WPL, which is the elastic modulus at y-axis. Okay, and then by using the elastic modulus, I try the section using this, and I list down all the data here. Then I will go through the material properties. So referring to the 3.1, the T is TF, thickness of the flank is 13 mm. So by referring this, 13 mm is less than 40 mm, and the grade is S275, and the Fy is 275, and the Fu ultimate tensile strength is 430. Okay, then we go through the section classification. Also refer to the table 5.2, and then yeah, this table. Okay, and then we also obtain the flank for this is less than, and the weight also less than. So since this two is class 1, so the section is classified as class 1. So next is calculate the shear force resistance. The shear force that I calculate is 150.6 kN. So to find the shear force resistance by using this formula, so before calculate, we have to calculate the shear area for the wet and the shear area for the max. and then we use the AV, which is more than, so it's 3153.3 millimeter square. Then we sub into the formula to get the shear force resistance is 565 kilonewton. Then we design check, and the shear force must less than the shear force resistance, so the section is okay. Next we go through the shear blocking resistance checking for the web. So if using this formula less than, so the shear blocking resistance no need to carry out. So therefore for checking the shear blocking resistance for the web is not required. Okay, then we check for the bending moment resistance. And the bending moment that I calculate is 257.75 kilonewton meter. So for the class 1, by using this formula to calculate the bending moment resistance. Okay, so sub all the data and I get 277.75 kilonewton meter, and the bending moment is less than the bending moment resistance. So for the design check is okay. Next is combined bending and the shear resistance. So we find the maximum, when at the maximum moment the shear force is 0 kilonewton, and then for the 0.5 shear force resistance is 250.325 kilonewton. So the shear force is less than the 0.5 shear force resistance, so the checking for this combined bending and the shear resistance is not required. And then we go through the lateral torsional blocking LTB checking. So because of our design beam is restrained, so this is not required to calculate the lateral torsional blocking. Okay, and lastly we go through the servicity limit check. Okay, and then I separate into three. The deflection one is the uniform distribution load for the deflection, and this one is the point load for the secondary beam, and this one the point load for the secondary beam too. And then I total up the maximum deflection, get the answer 6.58 millimeters. And the main beam DE is carrying the secondary beam, so I using this formula to get the answer 30 millimeters. So maximum deflection is less than the deflection limit, so it's okay. So I adopt the section list in grade as 275. So for the question 2, if the beam DE is unrestrained, so what will I do differently from the above beam that I have designed? Determine the bending blocking moment resistance. Is the beam safe to use? So by using the same triad section to calculate the unrestrained beam. So the in front of the step is the same, so I skip to the lateral torsional blocking. So first calculate the effective length. So I consider the segment BC is more critical and larger bending moment. So by using this formula, and I get the LCR is 2000 millimeters. So first I will attempt the C1, by using these two data, bending moment, the lower bending moment and the larger bending moment, and the C1 is 1.02, and then sub into the formula MCR and sub in all the data to get the answer. Then I will calculate the slenderness, also sub in all the data. Then I will determine the blocking parameters. So by using this one, H divide B, so referring to the table 6.4, this one. So H divide B is greater than 2, so is blocking curve B in the row I section. And because of curve B, so the imperfection factor is 0.34. So 0.34, and then we sub into this formula to get the answer. After that, we have to calculate the reduction factor by this that we obtain. Then lastly, we can calculate the moment blocking resistance. Okay, and the answer is 244.7 kilonewton meter. So the bending moment is greater than the moment blocking resistance. So this section is not okay, and the size of the beam should be increased. So for this section, it's not satisfactory under the lateral torsional blocking. So need the larger section should be used. So for this question, the beam is not safe to be used. Okay. So for the third question, if the office is designed not based on simple construction, so what would I do differently from the above beam that I have designed? So for the simple construction, we using this simple, so we using this formula, LCR equal to 1.0 L length. Okay, so for the continuous construction, because of the continuous construction, the joint is rigid. So we using this formula LCR equal to 0.7 LLT. So this is what the difference for me to design the continuous construction. So that's all for me. Thank you, Proof, for listening. Yeah, thank you.